So we finished up last time. I said we were going to introduce a couple of concepts. One of those is what we call a two-force member. So the idea behind there's what we call two-force members and three-force members. The idea behind a two-force member is for an object to be in equilibrium, for an object to be in equilibrium with only two forces applied, the forces must be, there's a few conditions on these forces. They must be equal and opposite. They must be collinear. And those are the two. Right? I guess there's really just two. It's, well, equal, 1, 2, it might be opposite, 3, collinear. Equal, opposite, and collinear. That can take, oh goodness, all kinds of variety of shapes. Let's say we will, a little bit later in the course, we'll see what we call truss members, which often look like just kind of planks, something like this, to where I've got some force, let's say force A, and some force B applied to it. For this thing to be in equilibrium, those two forces have to have the same line of action. They have to be collinear. Same line of action. So they have to be collinear. They have to be equal and opposite. Can be some sort of a mutant potato, so long as force A is collinear, equal and opposite with some force B. If either force is larger than the other, this is going to accelerate in the direction of the larger force. If they're not collinear, if one is off down here a little ways, notice now you've got a couple moments being applied to this thing, and this thing can rotate. So the moment is not zero. The only way for the sum of moments to be zero is for these to be collinear. The only way for the sum of forces to be zero is for these to be equal and opposite. And so that's what we're looking at here. This is L9, page 2 of something. Okay. I'm going to pause and see if I can straighten this camera. It's bothering me. I don't know if that's any better. I feel like it's better. We'll keep going. No, I'm not going to fuss too much with it. Okay. The other scenario, that is the concept of two force members. All right, so the other scenario to talk a little bit about, they talk about, at least in our text in chapter 5, kind of a special case is what we call a three-force member. Something with only three forces acting on it. So if a body or some object has only three forces applied to it, it can, wow, I can't write. Not that I can normally write, but if a body has only three forces applied to it, it can only be in equilibrium if, and there are two conditions. One condition is the forces are what we call concurrent. And that would be, I normally just draw this as a ring. We could draw some mutant potato if we like. Concurrent means that the forces, got F1, F2, some F3. Concurrent meaning that their line of action intersects. All three forces, their line of action must intersect. That is one option. They must be concurrent. The other way the forces are parallel. So the other way, we can have a system of only three forces, F1, F2, and F3. The only other way three forces and only three forces applied to something can be in equilibrium is if those three forces are parallel. You will still have to, this in and of itself, these two conditions in and of themselves do not guarantee a three-force member. But these are requirements. These are the only way, basically, that you're going to be able to get your moment equation to set to zero. And then the magnitudes of these forces have to be such that when you take your sum of forces in both directions, you find a zero sum. So the magnitudes are going to have to be mathematically dependent on each other. But these are the only two conditions with three forces and only three forces where you have any mathematical chance of possibly achieving sum of moments to be zero for the body. Okay. Another concept to introduce on when we start talking about equilibrium applied to rigid bodies is this idea of weight and center of gravity. So typically we can neglect the weight. Reason for that is often if you look back at the examples we've worked so far and you look back at the problems and the homework you've hopefully worked so far, how often do we account for the weight of a structure or an object? We normally don't, because normally the amount of force applied, the other forces involved, are normally going to be substantially larger in terms of the weight is going to be a very small percentage of the applied load if we did consider it. So it really wouldn't, very rarely does it have a significant impact. However, depending on what I'm working with, sometimes the weight will be a significant factor. Just depends on the situation. And so if you do have to apply a weight, just like you would have seen in a physics class, weight is going to equal the product of mass and gravity. We talked about units and dimensions the first day. We talked about pound mass versus slugs versus, and of course, kilograms and newtons in the SI system. Then there's going to be a term we call the center of gravity. We'll call that, in this text, they just call it a capital G. Other texts might call it something slightly different, but that's pretty common in a lot of statics texts that I've seen. They'll typically use a capital G. Now, a little bit later in the course when we talk about centroids. That's one of the later chapters. This is L9, page 3 of something. When we talk about centroids, there's, well, is the center of gravity at the center? That's an interesting question. So a lot of times, if you see the term uniform or constant density, these are terms used to indicate the center of gravity is in the middle, or the center, and often we call the centroid the location of the middle. So if something is uniform or constant density, then what they're doing is they're telling you just locate the center of gravity in the middle. And what that means is this is the location for the weight. Where do you apply the weight? Because now, again, because we're dealing with sum of moments, and those moments have moment arms, meaning I need to know distances and locations of forces. All that means where do you locate the weight? Well, you locate it at the center of a uniform structure, a uniform shape. Now, what you find then is the weight can essentially be treated as a distributed load, and if it's uniform, that means it's a constant distributed load throughout the object. And like we talked about with distributed loads, when I convert that into a singular force, and I just need to locate that in the center of the object, that's basically what we're doing here. Is we're saying treat the weight like it's a rectangular or constant distributed load, and locate it at the center if they tell you it's uniform or density or constant density. And in this course, this doesn't work everywhere. It's definitely everywhere. It definitely doesn't work in the real world. But in this course, unless they tell you otherwise, you are welcome to assume that it's a uniform structure or constant density, and that you can just simply locate if you need to deal with the weight. They'll make it really clear. If I'm not supposed to just locate the weight of some structure, right, if I've got some structure here leaned up against some sort of two surfaces, unless they tell me otherwise, I'm just going to locate the weight right there at location G. And so what I'm telling you is when you draw a free body diagram of this thing, right, let's say this is at some angle theta. So I'm going to locate the weight right here, straight down in the y direction on 2 dimensions, straight down in the z direction on 3 dimensions. I'm going to locate the weight right there. This appears to be a vertical surface, so I'm going to apply a normal force. Let's call this point A, and we'll call this point B. So I'm going to apply a horizontal normal force at B, and this is a force A, so I'm going to apply a force normal to the surface A here. This is theta from horizontal, so that means when I apply a normal force A, it's going to be theta from vertical to get there. Okay, so all that to say, when I'm dealing with weight and the center of gravity, again, we mentioned earlier, typically we neglect the weight, but if we don't neglect the weight, we need to apply it. We need to apply it somewhere. Where do we apply it? We apply it at the center of gravity. And unless they've told you differently, you're welcome to assume you just locate the center of gravity, G, right at the middle of the object. And then this becomes your free body diagram. And notice I can solve for at least 2 unknowns. If I can actually solve up to 3. If I know the weight, I could find B, A, and theta on all these. Anyway. I say that I would need to know these links, but anyway. That's a good stopping place. I think we've got some, let me look. I think I've got examples for the next couple of videos. Yeah, I do. I've got a couple examples to work.